Hello, I'm Darvis, and here's our research on the evaluation of dihedral angles in the twin boundaries of copper. My fellow presenters are Fina, Sahiti, Joseph, and Magan. So why are we researching copper? Well, copper is a relatively inexpensive material to get, and it has naturally occurring thermal twins, which makes sample preparation fairly straightforward. Additionally, a paper written in 1957 shows that it's possible to calculate the interfacial free energy ratio, which is a valuable parameter used for solving material applications by measuring the dihedral angle of twinning planes. And all of these things, twinning planes, dihedral angles, and interfacial free energy of copper, are related to a copper's crystal structure. So how do we describe a copper's crystal structure? Well, we use something called a unit cell, which basically describes a cell with atoms set at points within the cell. For copper, this is a face-centered cubic, FCC, which means that there are atoms at each of the vertices and an atom at the center of each of the 6 faces. In copper, an important plane to know is the 111 plane, which we'll see is important to the twinning planes that I'll explain. So what are twins? Twins is when a crystal structure gets mirrored, like in the picture on the top right. The twin boundary is where the plane gets twinned, which is the line down the center of the crystal. And when a crystal twins, it always twins back, which is why you see 2 distinct lines, like in the 2 combined pictures. So when you view twins under optical microscopy, you will always see 2 parallel lines, which represent twinning and then twinning back. And for copper, the most common plane that gets twinned is the 111 plane, as mentioned previously. And the method proposed in 1957 gives us a way to use the dihedral angle of the twinning planes to estimate the interfacial free energy ratio. This ratio gives us the twin boundaries energy in the numerator and the surface free energy in the denominator. And these energies, which is given in their names, are related to the different energies within copper. So one is related to the surface and the other is related to the twin boundaries. And there are many other ways to estimate the interfacial free energy ratio, but they're all very difficult. So we will be using an AFM to measure the dihedral angle and thus calculate the interfacial free energy ratio.
Now I'm going to be going over the sample preparation process. This process consisted of 3 parts: heat treatment, polishing, and etching. So the first one is heat treatment, where copper samples are placed in the furnace at a temperature of 800 and 900 degrees Celsius. The samples are left in the furnace for exactly an hour and cooled in the air thereafter. Heat treatment oxidizes the copper sample, oxidizes layers need to remove for OM observations. Heat treatment changes the size of the grains and twins in the sample, making it easier to observe twins under the microscope. The picture on the right is the image of the furnace that we use for heat treatment. Next slide. Okay. The second part is polishing. So copper samples are polished manually using different types of sandpaper after undergoing heat treatment. The different sandpapers are shown below, and they range from 300 to 3000. The 300p grit to 3000p sandpapers were used sequentially until a mirror-like surface was produced onto the copper. Polishing removes the scratches and the layer of oxidation that is produced by the heat treatment. Next slide. Okay, and the final portion is etching, and the etching procedure is used to bring up the microstructures, so the grains and the twins that we use to analyze in the microscopes. Etching solution is consisted of 50% nitric acid and 50% water. Etching is performed for various times ranging from 1 to 95 seconds, and we tested multiple times with different samples. Each sample is rinsed with water to seize any further etching, and samples are dipped in methanol to prevent residue formation. The picture on the right is an image of a copper sample etched for 90 seconds.
Okay, hold on. We don't have a student who, right? We don't have somebody who needs to narrate the slides. So I will do narration. So what we did, we did the characterization with optical microscope. You see the optical microscopes in the lab. We have metallurgical microscopes like Nikon and Olympus, and we have digital microscope, which is Keyence. Keyence has a lot of software processing on top of just regular optics, so which is very helpful. We also have 3D printer Prusa that we use just to enhance our understanding of twinning. So, okay, next slide.
It's hard to visualize twin boundaries, so our group decided to build a physical model using 3D printed unit cells. We used FCC, or face-centered cubic, unit cells to replicate the structure of copper. On Prusa Slicer, these unit cells were then sliced into different orientations, like 001, 110, and 111, which were then used in the model. Superglue was used to attach the prints together, replicating the twin boundary. The blue arrows point at 2 crystals, and the surface the white arrows are pointing at is a 111 plane. The twin shown in the leftmost image is mirroring the 111 plane, making it the twinning plane. Before heat treatment, the size of the copper grains were too small to observe under an optical microscope, so heat treatment was implemented. The first heat treatment was at 900 degrees Celsius. After repolishing, the copper samples were etched for 33, 60, and 90 seconds. Grains and twin boundaries were visible under the Nikon and Keyence. The straight lines seen in the images are a clear characteristic of twins. However, there were polishing marks on the samples and some areas indicated over-etching. The twins were also slightly larger than 100 microns, making them less compatible with an AFM. Using this information, we decreased the temperature of the heat treatment to 800 degrees Celsius. This meant that the twins would be smaller and a more optimal size. The etching time was also decreased, so as to find a time which would reveal the grain boundaries without the copper being etched any further. As planned, the twins were observable in a smaller size. There were little to no signs of over-etching, but a few polishing marks were still on the sample.
So from here on, sample preparation has to be improved to move on to the next stage for quantitative metallurgical work. And we also have to perfect our procedures to write up a standard procedure for using the Buehler auto polisher, which needs polishing cloth and suspension, and also for etching copper, which includes monitoring time with a stopwatch and rinsing in DI water for longer, and also using the furnace and heat treating process. In these few months of researching, we have learned how to heat treat copper samples using the furnace and how to adjust the temperature to obtain desired grain or twin size. We've also learned how to fully model a twin boundary using 3D printing, how to polish our samples using the Buehler polisher, and to thoroughly wash the samples after etching with DI water instead of lightly rinsing it to stop etching on the samples. And we've also learned that samples need to be stored in the desiccator to prevent further oxidation.
For future plans, we will first continue to finish the complete 3D model of our twinning boundary in our copper samples. We will also adjust the temperature of the heat treatment to 700 degrees because we're aiming for twins smaller than 100 microns, and we're also looking to grow twins of the size suitable to be analyzed by the AFM. We're also exploring a possibility of using the EBSD, which is the electron backscatter diffraction, with a third-party partner to identify the twinning planes. So we're also fundraising for an AFM, which is the atomic force microscope. This is so we can perform dihedral angle measurements and estimate the ratio of interfacial free energy of twinning crystals. The price range for the instrument is $20,000 to $250,000, but we're really only looking for $20,000 to $50,000. Any donations will be greatly appreciated, and donations of $20 can be used for little things like sandpaper for polishing our copper samples. No donation is too small.
Your references. Thank you for listening. We'd also like to extend our thanks to ASDRP, Dr. Starostina, the parents, and Kaden Webb. Are there any questions?